Yeah.
All right, well, hi, welcome to the field conference. My name is Jennifer Elick, and I'm from Susquehanna University. And I'm a sedimentologist by training. I started looking at this fire about 15 years ago, which seems like a long time ago since it's changed so dramatically. And what I'd like to talk to you today about are some of the changes that the fire has experienced and the landscape has experienced over the 15 years that I've been studying it. Just to get you up to speed, I don't know how much you all know about Centralia. The rock underneath you right now is from the Llewellyn Formation. And in the Llewellyn Formation, which is a heterolithic conglomeration of conglomerates, sandstones, anthracite, coal, and shale, there is a rock unit known as the Buck Mountain coal succession. And this is the rock unit that you're standing on right now. This rock dips to the north in this area at about a 20-degree angle. And I have just an illustration down here to show you that dip. This whole rock unit sits on top of the Pottsville Formation, which is in that direction, and in fact actually the Oddfellow Cemetery, the St. Ignatius Cemetery behind you, and the St. Peter's and Paul Cemetery just above are on the Pottsville Formation. So that is an area that is not subjected to the fire. The geologic structure that you're on right now is an anticline, the Locust Mountain Anticline, which plunges to the east, so plunging in that direction. So we're on the northern limb of the Locust Mountain Anticline. Just behind you here, starting from about the corner of the cemetery, which has been subjected by the fire, is a black shale, and then moving from the corner of that cemetery, you run into the coal, the lower unit of the Buck Mountain coal succession. There are 3 coal splits in this area. This is a drawing, a composite from a borehole that was taken over in this area just south of where we are, pardon me, just north of where we are. And there are 3 splits of coal. I'll refer to the lower unit as the lower Buck Mountain, the middle Buck Mountain, and the upper or ugly Buck Mountain. It's separated by some siltstone and sandstone, and siltstone and then capped off with a sandstone. And actually this whole succession you can actually see here forming the topography. So for instance, where our buses are parked, which is really nice, we're actually parked predominantly on the sandstone that is located right here. The coal, the Buck Mountain coal, that's actually all 3 veins are on fire, is in this pit off to the south of us. And the hill side that we're going to walk up is actually located on sandstone. The next layer of coal is just off to the north of this hillside, and there are subsidence features associated with that coal as well. So just to kind of illustrate what you should be kind of envisioning here, we have a coal fire, right? The anthracite coal is on fire, and like I said, all 3 veins are exhibiting characteristics that suggest that there is a fire. And I say this based on the fact that when I fly over using thermal infrared imagery, you can actually see the linear traces of the heat basically rising to the surface along the different breasts of coal that have been mined out. So this is a thermal infrared image that I took back in 2011, when the fire was still a little bit more hot than what it is today. The fire is off just to the north here in the subsurface, probably less than 100 feet below the ground, just below about 2nd Street. This is South Street right here, just to give you some perspective. And the heat from the fire basically is rising up along the mined out breasts of coal. So if you consider, for instance, my fingers being an example of the coal mine, or the coal that's underneath us, each finger represents a pillar, and each empty space between my finger represents a breast that's been mined out. The fire is down by my fingertips, and the heat is rising to my knuckles. You're at my knuckles. This is the fire front. It's moved from basically east to west and it has pretty much stalled out right now from thermal infrared imagery. And the fear right now is that, not the fear, the excitement, right, is that potentially the fire may start to move towards the north, jumping to the next overlying coal unit, which is the 7-foot coal, which may be 7 feet thick. So just to give you some more perspective, here is the St. Ignatius Cemetery, which is right behind you. The St. Peter's Paul Cemetery is right up on the hill. And this is the northern limb of the Locust Mountain Anticline. The pink to red structures here are the pillars that have been left, and the empty spaces between the pillars are the breasts where the coal has been removed. In 1983, Stanley Mikulski and the GAI guys basically were monitoring this fire and identified that the fire location, its hottest point in this area, was just about right in this location. At the time that I started really focusing on this fire in 2011, I figured that the fire had actually moved to be right about here. So just towards the top of this hill is where the hottest point of the fire is located today. But basically the fire has moved along a trajectory, probably along gangway number 2 and gangway number 1, making its way westward. You can see in this photograph that there are a lot of empty spaces where either the coal was mined out or robbed from the pillars, or the roof collapsed, and that has been an issue with regard to subsidence. Some other points that I want to make before we start walking up the hill is I've measured the gases coming out of the vents all along this trajectory. And in fact, actually, I started measuring the gases back in 2011. I'd like to tell you just a really tiny story, and then we'll walk up the hill. In January of 2011, I was silly enough to bring students out right after a snowstorm. And we had close to a foot of snow, followed by an ice storm. And I thought, oh, this is great. You know, we'll see some clouds of steam coming up from the ground, and that'll get them excited about science, right? So we parked here. There was no snow on the ground here because it had melted. But what I started to notice as I walked through this area with the students was that there were a number of new cracks. I've been coming here every semester for 15 years, and I saw new cracks that had formed on the surface, and I thought, well, this is kind of peculiar. I wonder if it has anything to do with the snowstorm. So I decided to come out here every time there was a snowstorm of any significance or a rainstorm that lasted over an hour or that dumped more than an inch of rain, which was quite a bit. In 2011,
oh yeah.
Just pull this poster out. Thanks, guys. We had more rain in 2011 than in any other year in recorded history in the state of Pennsylvania. This is 2011 in comparison to, let's say, 1996 or even 1972 when Hurricane Agnes came through. The rain was so great that it really influenced the landscape here in a very special way. You know, the temperature of the fire has gone down. And it's not as sexy as it once was. The temperature at its highest point that I've ever heard was measured from surface exhaust vents along this transect to be 540 degrees Celsius. You struggle to find a vent today that's greater than 60 degrees Celsius. And it depends on the time of year that you're actually measuring temperatures. The temperatures fluctuate on a daily basis. They fluctuate on a seasonal basis. So in the wintertime, they tend to die down just a little bit. In the summertime, they tend to rise up because there's a lack of moisture, precipitation influencing the fire. We actually have a seasonality component that's recorded by this fire. When we have heavy rains, like for instance here is Hurricane Irene and Tropical Storm Lee, the temperature of the fire actually dove down quite a bit, almost 20 degrees Celsius from its normal temperature. So this gives you a sense that this was a special year to have so much precipitation. When that precipitation interacts with the hot fire in the subsurface, what happens is it creates steam, right? And that steam comes up from the exhaust vents at the surface and interacts with the surrounding rock. What I started to notice back in 2011 was that some of these cracks were actually growing together and creating sinkholes. And over time, we could actually watch these sinkholes become deeper and deeper. And I'm just going to throw this out just for the sake of it. This is a graph showing the amount of precipitation for the different months in 2011. And this is one particular sinkhole that I focused on, and its growth. And I'm just going to point out this is sinkhole depth, which it doesn't seem like much. This is a 2-meter scale. But over the course of the year, this sinkhole became almost 2 meters deep and 13.7 meters wide. So it became quite large. And it's not the only one. There were about 7 new sinkholes along this pathway of the fire that developed. And I have right here, just to point these out, these formed along the trajectory of the fire and along the Buck Mountain coal splits that I mentioned earlier. So I noticed the interaction of precipitation and snowmelt basically was softening some of the rock that was holding up the surface and allowing that rock to basically collapse or succumb to gravity. And so what we're going to do is we're going to walk along this trajectory and basically look at some of those sinkholes. And I've got a gas meter in my pocket. We're just going to examine some of the landscape features while we're here at this stop. Do you have any questions?
Yes, ma'am. Is it a positive feedback loop where the sinkholes develop where there's water, but forming a sinkhole directs more water to accumulate there, which would cause it to self-amplify?
Well, that's an interesting question. It probably did self-amplify. You can see here we actually had a location where there was a puddle, and that puddle became larger over time, but the weight of the water may actually have helped promote the sinking of the ground.
Oh,
yeah, and
or
actually
infiltration of that water into the...
Or the infiltration, yeah. One way that I was able to actually see some of the sinkholes forming was by seeing puddles of water at the surface, and you could actually identify where the sinkhole was, in addition to the cracks.
How deep is the water table?
How deep is the water table? Ah, gosh. There's a mine pool that's at about, on maps it's at 1,000 feet, I believe, below the surface.
Elevation.
Elevation-wise, yeah. So I'm not sure exactly how deep. Maybe 400 feet below.
It's about
does this act like a wick?
feet below the center down here.
Okay.
It's pretty deep.
What does your gas meter measure?
My gas meter measures carbon monoxide, carbon dioxide, hydrogen sulfide, methane, and oxygen.
Thank you.
Mm-hmm.
Is it safe to like walk up to the vents? Like
yeah, actually, I think overall, if you don't, sit at a vent and suck the gas out. One of our colleagues actually analyzed the gases in a GSA meeting field trip about 10 years ago, and he found that there were 45 organic chemicals that were coming out of the exhaust vents here, and some of them are very toxic. The wind here is usually enough to remove those gases from you so that you should feel somewhat safe. Yeah.
Now, if it ignites the 7-foot pole, what then is the anticipated trajectory of the fire?
Well, then it may possibly continue to move back and forth east-west, and if it gets hot enough, the thing about coal fires, from what I understand, and I'm a sedimentologist, I'm not an expert in this by any means, but what I understand is that basically one bed of coal on fire can actually preheat the next overlying coal bed, even if there's a distance between the coal beds of 20-25 feet. If there are fractures in the bedrock where the heat can basically be transported to the next overlying bed and preheat it, that coal bed can start or ignite at a lower temperature than what it normally might ignite at. And so there's always a possibility that the coal fire can jump in that way. And so what I've been noticing actually are fractures that are north-south oriented that have developed at the top of the hill that tend to be colonized, number one, by moss, which tends to be a giveaway for exhaust vents. But number two, they're usually warm, giving off heat and gases, and they're generally moist from the steam and condensates.
Okay, and are they above that 7-foot coal, or are they still over the Buck Mountain?
They're still over the Buck Mountain. Yes, sir.
Where is relative understanding, where was the trash dump site when power started?
Over westward, or pardon me, eastward.
How far?
Well, I've been told it was right near or adjacent to the Oddfellow Cemetery. Back when the fire started, I was yet a dream in my parents' eyes. The fire started, was ignited in May 27th, 1962. And so I'm working on a lot of history that I've read about from other folks. But yeah, in that direction towards the east.
Were the seams mined independently or as a unit?
I'm sorry?
Were the coal seams mined independently or as a unit?
That I don't know. I would have to ask anyone else who might have some expertise in that. Anyone?
I have a quick question.
They appeared to be independent. They weren't columnized.
Okay. What? I have no idea.
This was independent.
Yes.
Is there any sort of hydrothermal alteration going on here with the fire and the interaction between the fire and groundwater or precipitation or anything like that?
There likely is at depth. At the surface, there were minerals that would precipitate.
Yeah.
Apjonite, sugarmite, different kinds of minerals that aren't normally associated with the surface. But in the subsurface, there probably is some alteration that you can study at some point.
When the fire goes out.
When the fire goes out. Anyone else? Yes?
I know at one time it was estimated that the fire could burn about 3,500 acres. That was in Office of Surface Mine reports before they relocated the town in 1983. Do you have any idea what the boundaries are now? Because I know they had it limited based on the mine pool, where it would get quenched or where it outcropped or where it was mined through. But do you have any idea what the boundary of it is now?
You know, actually, this actually might be even more helpful. So, one of the ways in which I know that the fire is moving towards the west is I've mapped it out. I've mapped the distribution of heat being given off at the vents using thermal infrared. And like I said, I haven't been around for that long. I've used other infrared images that the state has in its library. And basically, here's where the fire supposedly originated and has moved along both limbs of the Locust Mountain Anticline. The area, if the fire was to continue moving westward, from what I understand, the coal has been mined out in a westward direction, so there isn't an abundance of coal. And in fact, actually, Susquehanna University used to have a research area right in front of the fire. We anticipated its movement, and we're looking at the types of bacteria in the soil and the gases and the temperatures, and it just so happened that the fire stopped moving in this direction, and presumably because the fuel source just isn't there, and potentially also because the ground has collapsed in several areas in this direction, blocking the inflow of gas, oxygen that could be feeding the fire.
Where are we on this diagram?
We are located right now right about here on the top of this blue blob.
Was there any deep mining underneath the Buck?
Underneath the Buck is the Pottsville Formation,
Well,
which
those
is...
lichens are in there, but did they mine any of the lichens coal?
You've got me, I don't think so.
There are some headings in the lichens.
I know there are a few small coal beds in the Pottsville, but I don't think it's been economically viable to actually go after that.
More economically viable in like Dauphin County, Tower City area up here, they weren't.
There are exploratory headings in the lichens all along, especially on the south flank where you have the green.
Right here.
Yeah, the south flank of the Anticline. I mean, there's my map showing that. So.
Any other questions?
Right behind you.
Yeah.
Did you put the measuring for sulfur?
You know, my gas meter reads for hydrogen sulfide, and one of the things is I started measuring the gases in 2011, and honestly, the amount of carbon monoxide was really low, and I only got readings for carbon monoxide when we had a really significant rainfall event, which probably indicated that the amount of oxygen that was basically available to the fire had plummeted, and so you're generating more carbon monoxide. Generally, I saw no methane on my meter, and hydrogen sulfide rarely ever registered. Yeah, so we've got a lot of walking, so we might as well take a trip and see some of these sinkholes and features. Back in 2011, this is one of the locations where I started to notice the formation of sinkholes really prominently on the landscape. And if you just look in the distance here at the road, you can actually see how the road is sunk downward. That's accommodating a very large sinkhole that formed from the coalescence of 4 sinkholes that have grown together. Folks use this road to get to the cemetery, and yet they don't realize they're driving over not only a coal fire, but also a sinkhole. Let's take a look at it, but while you walk into it, look up above and along the sides of it, and you'll see there are cracks and fractures all along the side. We'll stick the gas meter in one of those holes and see what kind of readings we get. But this is where you will find a lot of heat being released along this particular series of sinkholes. If you follow the trajectory where Colin is standing and just walk along this kind of little pathway through the brush, you'll notice that you're walking along a very large fracture, and if you put your fingers down in the fracture, you'll start to feel some of the steam and gases that are coming out. That is one side of the sinkhole. And this is the other side of the sinkhole. It's a pretty large structure that has formed from the coalescence, thank you, of 4 small sinkholes. And it just happens that these sinkholes are all in alignment with the lower Buck Mountain coal. If we go over the hill, there's another series of sinkholes, and that's associated with the middle Buck Mountain coal succession. So we're on the lower part of the Buck, and in that direction, right over the hillside, is the middle Buck Mountain coal with sinkholes associated with it. So let's stick this in a fracture. All right, so I'm getting 21 oxygen, 0.06 carbon dioxide. Let's just sink this into the hole. The problem with this gas meter is that it's sucking air from the vents, but it's also sucking moisture, and very commonly that will complicate my readings.
Something out that long.
All right, so just so you're aware, the sounds that my gas meter are giving off is that we have reached a point of 19.5% oxygen and 0.66% carbon dioxide. And it seems to be stabilizing at about that point. I'm not getting any hydrogen sulfide, I'm not getting any carbon monoxide, or any methane. So I think that's a good reading. And there's one behind here. The poster that I showed down below that had a picture of a carpet in it, you can actually see the blue carpet on the side of the sinkhole structure. And now that sinkhole is probably, I haven't measured it recently, but it's probably about 3 meters deep from what it once was. We find fractures that are moist, that are covered with moss, that have caused my oxygen meter to fluctuate a little bit, not much. It's going between 21 and 20.9, so it's not a lot of a fluctuation, but there is a series of north-south oriented zones right through here that suggest that the heat is being released here in addition to the sinkhole behind you. There's a small sinkhole right in this area, and this is what is causing me to think that potentially, even though the fire has stopped moving towards the west, that it actually may potentially have the opportunity to propagate towards the north to the 7-foot coal. There are a series of little holes here where the heat is coming out right here, and this is a vented area, and it's actually an elongated area that follows probably some fracture patterns in the rock. So we're just going to keep watching this over time to see if this does pay out and that the next coal catches on fire. But right now, we only know that the Buck Mountain, the lower, the middle, and potentially the top are on fire.
Is there a potential remedy to this, that you could pressure grout the fractures shut?
I think actually part of what the people who are leaving the fill material here are doing is they're leaving material that other people are filling cracks in, and I guess that's always a potential to fill them in and maybe, you know, deplete the oxygen content.
Well, I was thinking of preventing from jumping to the next hole.
Oh, if it's a subsurface fracture, no. It's going to, unless you have really high pressure grout that can level and find its way and withstand high temperatures, I doubt it. We're going to, basically, I'll show you why I came to the conclusion that the precipitation was interacting with the hot rock and causing the bedrock at the surface that's holding up the ground to actually subside. So all around us, we're surrounded by this possible conglomerate, and conglomerate rock is relatively hard, right? Oh, yeah. Really hard. It's quartz cemented conglomerate. It's a real hard rock. So I take this rock hammer and just use the pick and gently knock at the bottom of this possible conglomerate. I easily produce a handful of pebbles. The constant steam from the vents, from the precipitation that's occurred, has basically caused this quartz cemented quartz conglomerate, pebble conglomerate, ortho conglomerate, to basically break apart. You know, you can probably imagine that some of these gases that are coming out probably have a little bit of acidity to them, right? And that acidity plus the constant heat and just steam itself is enough to allow for this conglomerate to easily break away. The same can be said for any shale that's in the area. Any shale that's in the area, if we start digging and find a piece of shale, it just molds in your hand like clay. It absolutely is turned to mush. And in 2011, that became really obvious here with all of the pebbles that were falling out of the rock that was situated at a vent. And this is a vent location. But this was just kind of confirming my sense that the precipitation was interacting with the rock and being leaving the vents and interacting with the bedrock around it and causing the bedrock to literally lose its rigidity, its hardness, and allowing for the rock at the surface to subside or collapse. Just happens to represent this forest that's come back. There were large fissures that developed in this barren field, and now it's colonized by birch trees, and they seem to be pretty healthy. You know, it's been since about the time of the drop of the fire, about 10 years, and they've had enough time to really kind of grow in stature. Stop1 is another sinkhole, and this is a sinkhole that I don't monitor for gases anymore, just because I haven't had any readings from the sinkhole. But it's right in here. You just have to watch for the ticks, right? But there's a large sinkhole. It almost looks like a meteorite impact structure. So folks, if you want to sneak in here, Stop E is located right behind these bushes. And what you can see here is a sinkhole that's easily 25 feet wide and a couple meters deep. And like I said, it seems to be an inactive sinkhole because we haven't had any temperature or gas measurements of any kind that can be registered by flying over.